In today's video, we are going to explore how the electric motor functions, a concept deeply rooted in what is known as the motor effect. As we have seen in previous lessons, if a current-carrying wire is placed within a magnetic field, that wire will experience a force. This interaction between electricity and magnetism is precisely what we refer to as the motor effect. The direction of this force is not random but is determined by the directions of both the magnetic field and the electric current. We can accurately determine the direction of the force using a simple yet powerful tool known as Fleming's left-hand rule. For example, when the electric current is flowing out of the page towards the observer and the magnetic field is directed horizontally to the right, the resulting force on the wire will be directed upwards. On the other hand, if we consider another wire where the current flows in the opposite direction, the force it experiences will also reverse direction, meaning it will now act downwards. Now imagine that we take these two wires and connect them together at the ends, effectively forming a coil. In this setup, current flows from the positive terminal on the right side, loops around the coil, and exits through the negative terminals on the left side. Due to the motor effect, the left side of the coil will experience an upward force, while the right side experiences a downward force. This combination of opposing forces causes the coil to begin rotating in a clockwise direction. However, there is a complication. Once the coil rotates by 180 degrees, the direction of the current in each side of the coil reverses. This means that the left side of the coil, which was previously being pushed upwards, now experiences a downward force, and the right side, which was being pushed downwards, now experiences an upward force. As a result, the coil begins to rotate in the opposite direction, or anti-clockwise, causing it to flip back over to its original position. This creates a problem because instead of rotating continuously, the coil would simply rock back and forth. It would not complete a full 360-degree rotation, making it impractical for most applications that require continuous spinning motion. To solve this issue, we need to reverse the direction of the current every time the coil completes a half turn. This ensures that the forces acting on each side of the coil remain in the same direction relative to the coil's motion, allowing it to keep spinning in a consistent direction. This is achieved by using a special device known as a split-ring commutator. For exam purposes, what you need to understand is that the split-ring commutator is responsible for switching the positive and negative connections every half turn. This action effectively reverses the current's direction in the coil at just the right time, maintaining a constant direction of the resulting forces. Because of this, the coil continues to rotate in the same direction with each complete turn. To better understand how this works, let us observe the entire setup in motion. When we connect the positive terminal of the power supply to one side of the commutator and the negative terminal to the other side, electric current begins to flow into the coil from the positive side, loops around the entire coil, and exits through the negative side. This setup causes the coil to experience forces that make it rotate in a clockwise direction. As the coil spins, the split-ring commutator rotates along with it, but the electrical contacts from the power supply remain stationary. This clever design ensures that the direction of current flow through the coil stays consistent with the direction of motion needed for continuous rotation. Although the setup might appear slightly complex at first glance, it is actually a fairly straightforward engineering solution and forms the basis for how most electric motors function. These motors are used in a wide variety of everyday devices, from household fans and vehicles to computer hard drives. The fundamental principle is that we can create continuous spinning movement using electric current and a magnetic field. Of course, in real-world applications, motors need to be much more powerful than the simple one demonstrated here. Fortunately, we can increase the speed of rotation and the overall power of the motor in several effective ways. The first method is to increase the amount of electric current flowing through the wire. The second method involves adding more turns to the coil, which increases the interaction between the magnetic field and the current. Lastly, we can increase the magnetic flux density by using stronger, more powerful magnets. All of these changes contribute to making the motor spin faster and with greater force. That wraps up everything for this video. I hope you found this explanation helpful and informative, and I look forward to seeing you again in the next lesson.